Garlik, and he'll give us the title of his talk is, as written there, Ajtai's Completeness Theorem for Nonstandard Finite Structures. Take it away.
Thank you. So good afternoon. I would like to thank the organizers for inviting me here. And I want to talk about this Ajtai's theorem and also mention some plans of my research here at the Institute. So I will start by stating the theorem. This will take some time. Maybe some more blackboards. So assume M is a non-standard countable model of Peano arithmetics. Formulated in the following language. Which consists of plus times less than equal to, then a special name for a certain non-standard element chosen from M, and then some other relations. And here these three symbols are thought of as relation symbols. There are no function symbols, they are relation symbols and only this one constant symbol. Next, assume that G is a recursive theory in language L, and assume G proves that less than equal to is a linear order. Then the following are equivalent. Condition 1 is that there does not exist a model N of the theory G such that the following structures denoted by these superscripts, which mean one structure is considered a substructure of the model N, the second of model N, and their domains are always in both models elements which are less than or equal to N. And the condition is that they are isomorphic. Let's denote the original structure in our model M by A sub N. And the condition number 2 is that there exists a proof P in the theory G plus a simple diagram or atomic diagram of the structure AN. Here we take all the atomic and negated atomic sentences which are true in this structure, about the elements of the structure. And this proof should have these following three properties. So property 1 is that P uses M rule. This thing is taken from Kotlarsky, Krajewski and Lachlan paper, and basically we add only this rule to some standard predicate calculus. So in addition to some standard rules of some predicate calculus which we fixed to some calculus, and this M rule looks like this. If we have derived some sentence phi about an element A for all elements A from our structure AN, then we can derive phi for all elements for x less than or equal to n, because that's the domain of the structure, phi x. The second condition is that we have some bound on this proof, and the bound is standard. So there is a natural number d such that the lengths of formulas which appear in P are at most d, and the length of the whole proof is less than or equal to n to the power d, where the length of P we can measure as the number of occurrences of atomic sentences. And the last condition is that P is first order definable in AN, in the structure AN, as some CRE relation. So it is a part of AN to the power C. So that's the theorem, and basically says that if you are interested in such extensions mentioned in point 1, then we must be able not to prove a contradiction inside the model AN. So it is an intrinsic property of the model AN if such an extension exists or not. And here I've written some simplified version of the theorem for the purpose of this talk, of the original Ajtai theorem, but nothing important is left out. And I will proceed by giving some examples where these model extensions can be interesting, and also some examples where this theorem can be used. So, first example would go like this: if we can arrange the following setting, which I will describe, then we would be able to prove NP doesn't equal co-NP. And the setting is this: we have models M which is M, which is a model of true arithmetics. All the statements true about natural numbers. And another model N, which is also a model of true arithmetics. They are both non-standard, and if we find a non-standard element N such that these two structures are isomorphic, which means the restrictions of plus and times are the same in both models, and another condition is that this N is kind of thicker than the model M, so it contains every element from here is also in N, and this goes up to some 2 to the n to the k for all standard case. And if we have a graph on these n vertices, which is in M or also in N, and if in M there is no Hamiltonian cycle and in N there is, then we have proved NP doesn't equal co-NP. Yes, please?
Just in the theorem, in this proof, what's it a proof of?
Which this proof?
Yes, so P should be a proof of contradiction.
Yeah, proof. Oh, thank you. It should be a proof of contradiction.
Okay.
Yes. So this is a known example where such extensions of models of arithmetics come into play, and now I will state another where actually similar setting can be established that such extension exists. And both examples I will mention are due to Ajtai, and the first can be about pigeonhole principle, the theorem that there are no constant depth polynomial size Frege proof system of this principle can be established by the methods of this theorem. And there we have the following situation. We are starting with some model M of Peano arithmetics, and we are given a non-standard N and some relation on N, and we are to find an expansion of this structure, expansion with one function symbols, which and the function in the new structure has to violate the pigeonhole principle, so it will be a mapping from n to n-1, and this can be found. This was found by Ajtai. The ambient model is a model of some bounded arithmetics, and another condition I didn't mention is that the induction should also hold for this new function symbol, for this new enriched language by this function symbol f. And now the third example, I will look more thoroughly at it, and it's also due to Ajtai, and this is about parity being not in AC0. And we proceed by contradiction here. We assume that parity is in AC0, then a well-known result in finite model theory tells us that this means that there exists a finite relational language L, a sequence of finite structures, L structures, such that the cardinality of domain of each AE is HI is equal I, and then there exists a formula which is in language L plus some unary predicate U such that for every E I and for every interpretation of U in AI, the following holds. In the structure satisfies the sentence phi if and only if cardinality of U is odd. So we start with this sentence. It's true in real world, so it's true also in the true arithmetics. And so we can choose a non-standard I for which it holds, and this is exactly the situation we are heading to. So let here be a model M of true arithmetics, and here's some non-standard element N, such that we have here the structure AN, and M thinks that phi is satisfied in AN, and also it's true in M that the cardinality of U is odd. Then we are able to construct another model of some theory G, model N, model G, and the theory G proves the following implication, that if in AN U is phi true and this formula par, which I will specify later, then cardinality of U is odd. And we will be able to construct such a model such that it's true in N that cardinality of U is even. So how do we express these things? These things like cardinality of some set is even or odd, we express by quantifying that there exists some bijection between our set and even or odd interval, respectively. And now let me get to this formula. This formula has to say that phi really defines parity. That is the following sentence: phi about u intersection with the empty set is negated, and phi about u intersect with I plus 1 interval, and there is this logical conjunction. If and only if u holds on I plus 1 exclusive or phi on u intersect I, when this means the interval 0 to I plus 1 and 0 to I. Now, what about this sentence? This is true in real world. It's true about this structure. These structures will be built to be isomorphic, thanks to the theorem. So it's also true in this structure. So both the premises are satisfied. So G thinks U should be odd, but U is even, and this is a kind of contradiction we were heading to. So these are the examples I wanted to give, and let me briefly look at some ideas how to prove this theorem in a neater way than Ajtai does, because his proof is very long, and I think it can be simplified using some standard notions of recursive saturation and resplendency. So let me remind what a recursive type is, or definition of a recursively saturated structure. A recursive type is over some structure is a set of formulas in one free variable x and some fixed parameters, and this set is recursive, phi I on omega, and it's finitely satisfiable because it should be a type, and this means that every finite number of these formulas, when they are given, we can find an x in the structure which satisfies them altogether. And recursively saturated structures are such structures that every recursive type is realized in them, meaning that for every type there exists an x in a structure which satisfies all the formulas from the type. And it's true that recursively saturated structures, when they are countable, they are also resplendent, and resplendency means that for if the language of our structure an is L, and we are given a formula phi, which also uses other predicates. Let me write one, for example, S, and this phi about S is consistent with the theory of the structure A, then there is actually an expansion of the original model AN where this S is realized in a way that phi S holds. So then it realizes phi. So this is a definition of resplendency. And do one simple thing I can show in the remaining time, which occurs in the proof, is that these structures AN, these are the non-standard finite structures from the name of the theorem, are actually recursively saturated. And for the proof of that, we need one thing we need is a definition of this symbol of satisfiability in our structure AN. And we have it because everything is done from the point of view of this ambient model M. And if we ask if a sentence is satisfied in the model AN, now from the point of view of M, all the quantifiers of phi become bounded, and we have true definitions for formulas of bounded quantifier complexity. So this poses no problem, and the statement which leads to the proof should be there exists x less than or equal to I, so for every, or S, so for every I less than or equal to T, AN satisfies phi I. Phi I are formulas from a given type, which we are to prove to be realized in the structure AN. And so we take this statement and x should be smaller than n, where n is the last element of the structure. This statement is true for all standard finite t. So by overspill it should be also true for some non-standard t. It says that there exists an x, and for this non-standard t, this x will be a witness that this formula holds, and also a witness of this type, because the I ranges to some non-standard number, so all the formulas of the time will be contained there. So this is the basic idea how to prove this recursive saturation of these structures, and it's only one small step in the proof of the whole theorem. So I think I will stop and ask if you have any questions.
Yes. Yes, I have a question. Did you consider there is another way you can try to unify the results is via Ehrenfeuer-Forsig games? Because, for example, the characterization of NP and co-NP, one of them, and the other one was about first-order definability of parity. In both cases, you have these Ehrenfeuer-Forsig games by Immermann, where duplicator has a winning strategy, and that applies when you have sort of arbitrary existential moves you can make. And I think if you simply play the game and use overspill, you might not need a recursive saturation, because actually what it really boils down to is that you can have like one model, countable model of, say, true arithmetic, and in that model you play the Ehrenfeuer-Forsig game on some graph, let's say, have a Hamiltonian circuit, as you mentioned, and the other graph doesn't have a Hamiltonian circuit, but because if NP equals co-NP, then the duplicator, he has a winning strategy in the game for any constant, for any standard constant number of rounds, but that by overspill you can also select a small non-standard number of rounds. And that sort of induces a projection from N, the whole structure. But it's just an alternative way, it's an outline, I mean, but I'm saying you might consider that.
I have thought of it, yeah, thank you.
It might not work with the pigeonhole principle though, but it certainly unifies some of the results. So.
Well, Ajtai is actually using games which are sort of Ehrenfeuer-Forsig games, but it gets complicated because of the inbuilt structure, of the inbuilt L structure.
But the point
and
is,
moreover, it's a lot of time to actually get, it's not just the question of to construct this model, but also to get the characterization, the part 2 of the theorem, the complete.
But the point is that you don't need the recursive saturation, because the point is that the assumption itself, I mean, the very fact you assume NP is different from co-NP,
yeah,
is a very strong
but the
assumption.
point here is not to construct the things, but to prove this theorem, that the existence of such a structure is equivalent to this, completeness statement. And to get from the games these proofs is fairly complicated.
Then what you get from the games is simply that you get an equivalent formulation of NP versus co-NP. I mean, you say it's Immermann's definition, and then you can restate it as the existence of two non-standard models.
But that's just not good enough. I mean, you have simply a different situation, and this first one, NP to NP, is just one of them. What you really need is a characterization, as in Ajtai's theorem, of statement I. So you need something like 2. And this comes fairly easily.
No, but it's the same. It's the same. It's just another proof of Ajtai's results. I mean, I'm not claiming a new result. I mean, I'm just claiming.
So how do you get from the Ehrenfeuer-Forsig game the proofs he mentions in item 2?
Well, you get first of all you have one countable non-standard model M, and then you get a projection from that to in some sense a copy of itself, but where you are shifting around elements below N. So, but you're shifting down all the.
So what you are describing is that if NP equals to NP, how we could construct a model where we would possibly add some Hamiltonian cycle if it was not there before.
But it goes both ways, of course, because Immermann.
Well, whatever. But it's simply one of these examples. But it's not this general.
But it also unified, yes, because the other game with the first order definability, that you also have an Ehrenfeuer-Forsig game where you don't have the second order structures. I mean, you just the duplicate again can win.
Well, so you are saying that this Ehrenfeuer-Forsig games is a simply universal way how to construct models, and you can construct, and if there such a pair of models exists, then you can always do it by these Ehrenfeuer-Forsig games. That might be true.
That's what I'm
and
saying.
In fact, that is, but that's not the theorem. The theorem says that such models do exist if and only if some statements about probability, and you don't get that from Ehrenfeuer-Forsig games. At least not simply.
Well, anyway, I think.
Anyway,
I think we should. I think we should just speak.